Hello everybody. The topic for this video will be probability involving counting methods. Before we get into the examples, let's go over the counting methods that we're going to need to answer these questions. So the first one is the fundamental counting principle. So remember the fundamental counting principle, what we're really looking at, oh that's a little bit thick, let's make that like this. What we're really looking at is we have a series of decisions, and then we're going to have choices for those decisions. All right, so that's fundamental counting principle. And we're multiplying these numbers together, by the way. So that would be 20 times 3, so 60. Next, so I guess I can put a little 1 here. The other one would be permutations. So remember, with permutations, order matters. So when you're using all the items listed, that's n factorial, n being the amount of elements we're looking at. When we're using some of the items, that is when we get into NPR. N would be all the elements under consideration, so all the elements we're looking at, and then R ends up being how many of those elements that we need to fulfill whatever we're doing. And then with repeating permutations, remember that is n factorial divided by those repeating elements. So that can change. That's not an exact formula. The bottom part can move, or it can change, sorry. And then finally, the third thing we'll need is combinations. And remember, that's NCR, and the N and the R mean the same thing as I did with permutations. What I forgot to mention here at the start, though, that order doesn't matter. Order does not matter. So the previous chapter to this would have been focusing on these counting methods, so we're going to have to recall some of that knowledge for these probability questions. Okay, our first example. 2 cards are selected without replacement from a deck of 52 playing cards. Determine the probability that both cards are kings. Now, another way to look at these types of questions is that these are all single event situations, meaning they grab 2 cards. That was the event. I'm just grabbing 2 cards. And I'll keep highlighting that because that might help differentiate when we get into some other probability methods. So, for probability, reminder, and we looked at this before, but the probability of an event happening is the number of favorable outcomes over the number of total or number of possible outcomes, whatever you want to say. Okay, so now, in this situation, the favorable would be selecting both cards that are kings, so 2 kings. So before I even get into that, I guess I should start to think about, well, am I going to be using a fundamental counting principle? Am I going to be using permutations or combinations? Well, in this question, I could actually do it 2 different ways. So we could use fundamental counting principle as well. Yeah, we could use fundamental counting principle as well, but what I'm going to choose to use is permutations or combinations. So what we have to identify is if we have cards, a card hand, and we're looking at these 2 cards, and I could say this is or I'll say 3 cards. I have a 4 card hand here, A, B, C, D. If I switch the order of those cards, is that the same set of cards or is it different? Well, that would be the same set of cards, meaning the order of the cards doesn't matter, which is telling me that this should be a combinations question. Okay, so I know I'm going to be using combinations. Now, how many, so the favorable outcome again, sorry, is getting 2 kings. And how many kings are there in a deck? There are 4 kings, right? So in my NCR, here's my NCR, and I'm looking at the N. Well, how many kings really are there under consideration? There are 4. We have 4 to choose from. In the favorable, we get really specific, okay? So we're just asking about kings. So how many kings are there? There's 4. Now, how many kings do I need for this situation? I need 2. So 4C2 is going to end up being the expression for the top part of my fraction. Now, for the number of possible outcomes, well, now we're wondering, well, how many cards are there total? Instead of just how many kings, because kings was favorable, just how many total cards are there? Well, there are 52 playing cards. And of those 52 cards, how many do I need? I still just need 2. So that's how I'd express the second part, or the bottom of my fraction, and then I would calculate it, and I'd reduce it, and this thing's going to work itself down to 1 over 221. So that would be the probability for this situation. All right, example 2. In a card game, you are dealt 5 cards from a pack of 52. Okay, so I'm just going to highlight that. I went wiggly line at the start, then I went straight. When you look at your 5 cards, what is the probability that you have in this first question? I can even put a little A here. 4 aces. Okay, well, again, this is a card question. Whenever you're dealing with card hands, which are really just the group of cards you have, the order does not matter, just like we showed in the last one. So in this, I know I'm going to be using combinations. And again, this is really just a one kind of event situation where we're just being dealt our cards. Okay, that's the one kind of overall event. So probability of 4 aces, I'll put 4A. Okay, and again, it's favorable over total. So the favorable situation is that we have 4 aces, right? So to have 4 aces, let's think of, I'm actually going to bring in some fundamental counting principle here. These are going to be my aces. And then this, we're going to need a 5th card, so this will just be whatever other card that I require. So for aces, we just focus on aces. Again, we're going to be thinking NCR. Now, why am I thinking NCR, by the way? Because, again, the order doesn't matter, right? That's why I'm doing that. Sorry, I paused there because I just remembered I did tell you that. So the N value. So how many aces are there in the deck? Well, there are 4. And then the R value, well, how many of those do I need? Well, actually, in this case, I need all 4. Now, that gets me 4 cards. I need a 5th card because it says we need 5 cards in this hand. And it doesn't say what that 5th card has to be, so it can be anything. So then N value again, well, how many other cards are there? Well, there are 48 other cards. Why? Because there's 52 cards in the total deck. And then of those 48, how many do I need? I just need 1. And why do I need 1? Because that makes my 5th card. Now, that's the favorable, the aces and the other. The bottom part is just the number of total or possible outcomes. So just how many different 5-card hands can I have? So how many cards am I looking at? Well, now I'm going to consider all 52 cards, and I'm going to need 5 out of that set of 52. So that would be my probability for A. B. And yes, you guys can do the math and figure out the rest of the fraction. When I'm correcting, I'm going to look to see if I can see something like that. Also, if you write it in fraction form, it's nice to reduce it, but if you can't reduce it the whole way, that's okay. And you can always convert these things into percentages as well. Okay, B, 4 tens and an ace. Okay, so probability of 4 tens and an ace. I'm just going to put A here, guys. I'm not going to get too fancy with that. So favorable, 4 tens. So I need the tens. And then we need an ace. So again, I'm bringing fundamental counting principle into this. So how many tens are there? Well, there are 4 tens in the deck, and I'm going to need all 4 of them. And then how many aces are there? Well, there's 4 aces in a deck, but I only need 1 of them because that's going to make my 5th card. And then the bottom, remember that's how many possible outcomes. Again, that's just how many 5-card hands. That's not going to change from the last question. I'm going to consider all 52 cards now, and then I only need 4. Okay, and again, I'll let you guys work out that fraction. C, I guess I can call this. Sorry, guys. Not sure if I like this slide, this setup, whatever. C, same example, everybody. So it's still example 2, same situation here. Now I want a 10, a jack, a queen, and a king, and an ace. Okay, so those are my 5 cards. So I'm getting more and more picky. So again, I'm just going to say the probability of this, if A is going to be getting these 5 things. And we're just going to go through it. So I need my 10s, or A10, I guess. I'll need a jack. I'm going to need this king. I missed queen there. I'm sorry. That will be my queen. That's my king. And then that will be my ace. All right. So how many, and seeing we're dealing with cards again, you guys, we're still in this combinations question. How many 10s are there in a deck? There are 4. I need 1. How many jacks are there? There are 4. I need 1. How many queens? 4. I need 1. Pretty repetitive, right? You can tell that all of this is going to be the same. There's 4 of all these cards. So that's the numerator of my fraction. That's the favorable. Now for the total or possible, again, it's just 5-card hands, so that is not going to change. I'm not being picky. I just want how many 5-card hands. There's 52 cards in all, and I want 5 of them. Okay, and again, just calculate that, and you'll have your final answer. D. D says at least one jack. Okay, so at least one jack. Whenever you see at least, that's going to tell us it's cases because there's more than one way to accomplish this condition. You can have 1 jack, you could have 2 jacks, 3 jacks, and 4 jacks. I guess you could have 5 jacks, you might be thinking, because you have 5 cards, but there's only 4 jacks in a deck, so you cannot have 5 jacks. You can only have 4. Okay, so now how would we do that? Like I said, you can just go through the cases of 1, 2, 3, and 4 jacks. Or another way of doing it is if we determine the probability of no jacks at all, and we subtract that probability away from 1, that would leave us with just the probability of getting some sort of jack. So I'm going to do it that way because that is a little bit quicker. So I'm going to actually look for the probability of not getting a jack. Okay, so I don't want a jack, right? That is my favorable outcome. Well, how many cards are not jacks? Those are the ones I want to focus on. Well, there's 48 of them because there's 4 jacks. I take those away. There's 4 of them. 48, sorry. And then of those, I need 5 of them. The bottom, the total or possible. I'm sorry, I'm tripping over my words here. All the possible outcomes. Now I can consider jacks and all the other cards. So I'd have 52 cards left, and then 5. All right, and then to determine the probability of at least one jack, I'd go 1 minus whatever that fraction ends up being. 48C5 over 52C5. So whatever that works out to be, that would be my answer for this question. The other way of doing it, like I said, is you can find the individual probabilities and then just add those up. So whatever you want to do, but this is kind of a nice short way to do it. Example 3. I see I have a little typo here, sorry. The word counted has been spelled using Scrabble tiles. 2 tiles are randomly chosen one at a time and placed in the order in which they're chosen. Determine the probability that the tiles are CO. Okay, that's our first one. So this will be A. So the probability that we have this CO. Okay, favorable. Well, how many different ways can they pull out a C then an O? There's only one way you can do that. You just pulled it out because you can see there's not multiple C's or multiple O's. There's just one way we can do that. So that's favorable. Now over total, when we think about it, we are, again, if I go back to just drawing these letters here, okay, so that'd be one kind of spelling, I guess you could say. If I switch my order up, is that a new spelling or is that the same spelling? That is a different spelling. So order is going to matter here. So we're going to deal with permutations in this question. Okay, so of these, how many letters do I have, I guess? You know, I want to back it up even further. I'm going to use NPR. Why am I using the NPR? Because of all the elements I have, I'm only using some of them. So if I was using all the letters, that'd be my n factorial, but I'm just using some of them. So now for the n, how many letters under consideration? Well, there are 1, 2, 3, 4, 5, 6, 7 letters. And of those 7, I need 2. All right, and then we could just calculate it. And I wasn't calculating those previous ones. Here's one that's real quick, but you just get 1 over 42. Okay, so again, your calculator is likely doing that part for you. Now let's move on to both vowels. Okay, we want vowels. So again, order's mattering here. Okay, and if we look, I can count 1, 2, 3 vowels. So I don't need all 3 though, so I'm just taking some. So I'm going to use NPR again, and of the 3 vowels I see, I only need 2. On the bottom, that's the number of possible outcomes. However, I'm just going to grab any 2 letters again. I'm not worrying about vowels. So then there's 7 letters in play, and I'm going to grab 2 of them. So the top again was specific. I'm worrying about vowels. On the bottom here, it's general, just grabbing any 2 letters. And again, something like this, 3p2 is 6, and we still have 42 on the bottom. So this will reduce down to 1 over 7. Okay, so that's what you do if you have to get into the numbers as well. Example 4. Gwen, Morgan, Arthur, and Kay are volunteering along with 5 other students to be on their school's math team. That is a great thing to try to do. All the students have equal ability. Determine the probability that Gwen, Morgan, Arthur, and Kay, along with one other student, will be chosen to fill the 5 spots on the team. Okay, again, let's determine, if order matters or not. So if I have Gwen, Morgan, Arthur, Kay on the team, and one other, I'll put an O there. And then if I rearrange the letters, is that the same team or a different team? That would be the same team. So the order won't matter. Okay, so we know we're going to deal with a combination. So we're going to deal with that. Okay, so probability of having all this happen. Again, I'm just going to be lazy with my notation. Go back to just putting an A here. So favorable over total. Favorable would be these 4 people making it and one other. So I want these people, so G, M, A, and K, to make that thing, make this squad, and then just one other person. And then we'll have the possible outcomes, total possible on the bottom. So that looks a little bit like an R, that G, but anyway, how many, for the N, how many people am I considering? Well, I'm considering just these 4 people, and then how many of them do I need? Well, I need all 4. For the other position, well, how many people am I considering? I'm considering the 5 other people. It says there's 5 other people. And how many do I need? I just need 1 from there. Now, on the bottom, it's just how many 5-person teams could I make? Well, in general, there are 9 people interested in this team, and then I'm going to want 5 of them. So again, then you can go through and do your math, and here are the values that we'd get. So it would be 5 over 126, or you could convert that to a percentage as well. But again, this is all the thinking. Everything else after there, really, that's just calculator work. So that would be the probability that those 4 people, along with one other student, will be chosen. There are 18 bikes in Marnie's spinning class. The bikes are arranged in 3 rows, with 6 bikes in each row. Allison, Brett, Carol, Doug, Erica, and Franco each call the gym to reserve a bike. They hope to be in the same row, but they cannot request a specific bike. Determine the probability that all 6 friends will be in the same row with Allison and Franco at either end. Okay, so a couple things. So just the how this really shakes out. So here's a row 6. Here's a row 6. Here's a row 6. So that's the 18 seats that are in this spinning class, just so you kind of get that. Now they're wanting to be in the same row. So we're just going to focus on kind of one row at a time when we do this. Now the nice thing about this, well, actually I won't even say that. We'll kind of come to that in another minute or two. So let's look at, seeing there's 3 rows, there's technically 3 cases for this. Okay, so let's look at row 1. So I'm doing a case for each row. Okay, and why? Because there's 3 rows, and these guys are worrying about being in the same row. They don't care if they're in the first row together, second row, or third row. Now, I guess we should determine if the order matters. So you might be thinking, well, as long as they're in the same row, these 6 people, they're not gonna care. So if it was mess up my order, it won't matter because it's the same group. I think I missed somebody there, but I'm not going to worry about it. Oh, there's C. So it would seem like it could be a good combination. It'd be a combination question. But at the very end here, it says Allison and Franco are at either end. So they actually care about the order. Okay, they need Allison and Franco to be at either end. So this one will be a permutation question. Okay. Now, there's different ways to do this one, but sometimes I find these questions are a little bit easier. I'll put a 1 for row 1. Just to use fundamental counting principle on. So I'm going to put my 6 spots here to represent, well, these are my decisions that have to be made, but these are the positions, these are the seats in that row. Okay, and we know we need to have Frankie or Allison in that in the first and last positions. So for the first position, I would say, well, whoever got there first between them would have, or sorry, there'd be 2, either of them could sit in that first position, and then one of them would sit there. Let's say it was Frankie, so then the other person would be forced to sit on the other end. So the first person there would have 2 choices. They could sit on either end, and then the last person of those 2 would have only 1 choice. So that'd be the way to do that. Then we have these other people. I guess, so we've already dealt with Allison and we've dealt with Franco. So now Brett, Carol, Doug, and Erica. So for whoever comes first out of those four, he'd have a choice of 4 seats for the first position. 3, 2, and 1. I feel like I'm tripping over my words in this one. I'm sorry, you guys. But there'd be 4 different people that could sit in this position, like Brett, Carol, Doug, or Erica could sit in that second seat. Now one of them would sit down. Let's say it was Brett. Then there'd be 3 people left for that seat, 2 people left for that seat, and then only 1 person left for that seat. So that's how I would do that. Now, for the total on the bottom, well, again, we're saying it's permutation because order matters to these people, that there's going to be 18 people in this class, and of those 18 people, I need 6 to fill this row. So that is how I would do row 1. Now, if you think about it, row 2, so this is row 1, row 2 and row 3, they're going to have the exact same math going on. So I could do the exact same thing 3 times, or I could realize that, I could realize that and just put times 3 on the top of one of them and kind of save myself some work. So then when I do that, I would get, that's 8 and 6, so 48, 48 and 3, I think is 144. And then 18p6, I had to go to the calculator for that. That is how I did that, and that would be it. So there's a very small chance that if you can't reserve a bike, there's a very small chance that these people would actually get all in the same spot. Now, you might be thinking, well, as long as they get there super early, they should be good. You're right, but I guess we're assuming that everybody enters the room at the same time. Again, so I saved myself some time by doing this multiply by 3 because I knew that they're all 3 cases at the exact same math. But if you didn't do that, what you would do is you'd work out row 2, okay? And row 2 would have the exact same math, except I wouldn't count this part now. So I would have 8 times 6, so it would be 48 over that big number. Row 3 would be the same exact thing because the seats don't change. So it would be the same math going on. And I'd add the 48 up 3 times. And when you add 48 up 3 times, you're going to get this 144 over that big number. You're going to get this number here. Okay? And you can attempt to reduce it, or you can convert it into a percentage. I don't care. Okay, so that's all the examples I have for counting methods. Unfortunately, counting methods is something that you just got to do a whack of problems because everything, or there's just lots of variations in them. I've given you 5 examples, but that by no means kind of, I haven't been able to highlight every possible type of question. I just can't do that. So if you have questions, make sure you come talk to me. Have a great night, everybody.